Our first objective is to find the work done by a constant force. Generally speaking, work is done by a force when it moves an object. That can be pushing it, pulling it, lifting it. If an object is moving, then we know that work is being done. When we're applying a constant force, we find work by simply taking the product of force and distance. Work is equal to force times distance. For a lot of our purposes, we're going to be interpreting force as weight. So in a lot of the problems, when we set up work is equal to force times distance, we're really thinking of, well, how much does the object weigh and how far is it moving? For example, in problem 1A, we want to find the work done in lifting a 50-pound object 4 feet. We have the formula that work is equal to force times distance. I'm going to reinterpret that as work is equal to weight times distance. They tell us explicitly that the object weighs 50 pounds and that the distance it travels is 4 feet. So we take 50 pounds and we multiply that with 4 feet to get an answer that the work done is 200 foot-pounds. Foot-pounds is one of the units of measure for work, and we'll see some other ones here. In this table that summarizes different systems of measurements, U.S. International CGS. For example, here we see foot-pounds, common unit used in the US, where force is measured in pounds and the distance is measured in feet. We may see different problems where force is measured in newtons, distance is in meters, and that would mean that our final product of force times distance would be in work. So this table summarizes some of those conversion factors in different systems that we could be working in. Here we'll see another example where we're looking for the work done by a constant force of 112 newtons to slide a cement block 8 meters in a construction project. We're using the same formula as before, that work is equal to force times distance. Force is 112 newtons. The distance that it travels is 8 meters to give us a final answer of 896. When we take newtons and multiply them by meters, our resulting answer is in joules. So it takes 896 joules to move that cement block 8 meters. Our second objective is going to be to find the work done by a variable force. And this objective is really our focus in this section because when we're working with a variable force, now we need calculus to be able to determine how much work is done. Our formula is going to involve an integral, which should not be a surprise to us because Chapter 7 has been all about using integrals in applications, using integrals to find volume. Now we're using integrals to find work. I'm going to jump into our first example where we're going to see how this formula is going to be illustrated. This formula tells us that work is equal to the integral from a to b, that's how far the object is moving, of f of x dx, where f of x is the force function. It's a variable function. It's changing. It's no longer just a plain number. It's not like back in examples 1 where a cement block only weighed, we had a constant force of 112 newtons being applied, or we knew that we were only lifting a 50-pound object. Now we're talking about something where that weight is going to be changing. The amount of work that we're going to need to do will be calculated with an integral. So in example 2, we're looking for the work to compress a spring. They tell us that a force of 30 newtons compresses a spring 0.3 meters from its natural length of 1.5 meters. Find the work done in compressing the spring an additional 0.3 meters. Because this is a spring, I automatically know that I'm going to need to use Hooke's law to calculate this. And there's information about Hooke's law above here. So take a second and read number 1. They tell us that the force that we need, the force function, looks like KD. K is some proportionality constant, and D is the distance that the spring is being compressed or stretched. I'm not going to use D when I set up my integral. I'm going to use X because we're more familiar with just working with X when we integrate. So X is the distance that the spring is being compressed. Number one tells us that the K value is a proportionality constant, and it depends on the specific nature of the spring. So K can be different for different springs. Some springs are easier to compress. Some springs are more difficult to compress. Let's see what the K value is for this spring. So to find it, I'm going to use the fact that a force of 30 newtons compressed the spring 0.3 meters from its natural length. That means that when F is 30, when the force is 30, I don't know what K is. I don't know what that proportionality constant is, but I do know that the spring was compressed 0.3 meters. I can take this equation and solve for K to see that K is equal to 100. So now I know that the force function for this specific spring, f of x, is not just kx, it is 100x. So now that we know the function, we can go and calculate work, because work is the integral from a to b. I'm looking at this formula here of f of x dx. We just had to do a little bit of spring work off to the side using Hooke's law to figure out what f of x was. So now let's talk about what our limits of integration are. Well, the spring has already been compressed 0.3 meters from its natural length of 0.5. So right now it's at 0.3 meters compression, and we want to take it an additional 0.3 meters. So it's right now been compressed 0.3, and we want to compress it to 0.6 because we want to compress it an additional 0.3. I'll put in the force function that we found, and now this is a very simple integral for us to calculate. I hope you notice a theme throughout this chapter that we set up integrals using new concepts like volume or force or things like that, and then we integrate them using techniques that we learned back in Calculus 1. So this chapter is really about, are you able to learn these new concepts and then apply them as you already know how to? So I've just applied the fundamental theorem of calculus to get my final answer of 13.5 joules. And I know that my unit is joules because we had newtons and we had meters, and I'm thinking about the conversion table from above. In this example, we have a 20-foot chain that weighs 5 pounds per foot, and it's lying coiled on the ground. So that we have a chain lying on the ground. We want to know how much work will it take to raise one end of the chain to a height of 20 feet so that the chain is fully extended. So we'll take the chain, we'll pull a little bit of the chain up, then we pull a little bit more of the chain up, and then eventually the entire chain has been extended. Now, if we think about this chain, say we think about the beginning of the chain. Let's say I mark that piece as the beginning of the chain, that part right there. That red piece had to travel the full distance from the ground along this horizontal axis here up until 20 feet up in the air. But there's other pieces of the chain that don't travel the full distance. They travel a little bit less than that. So there are things that are changing in this problem, and so we do have a variable force. So to help us evaluate how much work is required, we're going to cut this chain into slices. So I'm going to take a slice of the chain of length delta y, a small slice of the chain, and let's figure out how much work was done on just that slice of the chain to get just that slice of the chain all the way extended. So right now I'm just calculating the work done on that slice. The work done on that slice is equal to the force of that slice, or the weight of that slice, times the distance that that slice had to travel. And then we'll integrate over all of these slices of the chain. So for the force, we're thinking of force as weight. Let's figure out how much that slice weighs. Well, the slice is delta y units long, and they tell us that the chain weighs 5 pounds per feet. So we have 5 pounds per feet. For every foot, we have 5 pounds. Well, how many feet do we have? but we have delta y feet because that's how long that slice was. So that gives us the weight, because notice that feet and feet cancel out and we're left with simply 5 delta y, and that is in pounds. Now let's go see how far of a distance that slice had to travel. Well, that slice had to travel this distance off the ground. I'll call that distance y since it's a vertical distance. So the work done on one slice is the product of 5 delta y, y. We need to integrate over all of the slices. The delta y is going to turn into a dy. So you can think of this product here as 5y delta y, just moving things around, just switching the y and the delta y because multiplication is commutative. And the delta y part is going to turn into dy when we integrate. So we have the integral of 5y dy. Now, what are our limits of integration? What values does y range over? Well, as we've seen, some pieces of the chain, like the very top of the chain, have to travel 20 feet to get to their final destination when the chain is fully extended. And then wherever the bottom of the chain is, well, the bottom of the chain never moves at all, doesn't travel at all. It always stays on the ground. So y can range from 0 to 20, the length of the chain. And now here we have an integral that we have set up and that we know exactly how to integrate this. We use the power rule and apply the fundamental theorem of calculus. So our final answer, we have 1,000. Let's think about the unit on this. We are working with, remember that work is force times distance. Force, weight, was given to us in pounds, distance in feet. So we are working with 1,000 foot-pounds as our unit.